Measurements and Measurable, Part 1. Why talk about measurements? Well, science in general is precise, and precise is being quantitative. Our everyday language, be it French, English, Bengali, whatever it may be, it is not designed for precision and logic. We therefore need a new language, the language of mathematics, and mathematics deals with numbers. Measurements assign numbers to the properties of matter, for example, temperature, density. Also, it assigns number to physical phenomenon, for example, movement. Science always seeks to quantify everything it deals with. It even quantifies correctness and flaws. All physical laws are testable, and statistically one can talk about the correctness of laws. So, can we measure everything? Of course not. For example, kindness of a person is not measurable. It's a qualitative statement. That's why there is no precise definition of kindness either. If we cannot quantify something, we either find a way to measure it or, for the moment, keep it outside the domain of precise science. So, what is the scheme of science? Where does the theory fit in? And what does the experimentalists do? Science basically has this scheme. You start with an experiment and gather some data. You then take this data to the theory and hope that from the logic alone, you will be able to produce a model which is capable of explaining this data. Finally, you bring the model back to the experiment and gather some new data. If the predictions and the data agree, the model stays. Otherwise, the model is rejected. Sometimes the situation gets so messy that the underlying theory itself has to be rejected. Consider measuring the frequency of a pendulum. You will need a stopwatch. Run the stopwatch for some time and count the number of oscillations within that time. Process your data, that is the count and the time, with the frequency formula and thus obtain the frequency. Here, you are measuring two things, number of oscillation and time interval. No matter how complex an experiment is, it always follows the same structure, same basic algorithm. So, as an input, you give it some values of measurement, and as an output or result, you get some values back. Both the measurement and the results are numerical data. What is this measurement then? Basically, a measurement procedure follows these three steps. First, you standardize a basic unit of measurement. For example, if you are measuring length, you might choose a unit of meter. Then, find a suitable apparatus. For the sake of length measurement, a scale will do good enough. Finally, the object you are going to measure, compare it with the unit you just standardized and come up with a result. For example, here we have 1.67 meter. It is just another way of saying that the object is 1.67 times the meter we have just standardized. And yes, you are free to define your own unit system. So for example, you might come up with a new unit called sitter. However, since all the laws of physics are to be discussed in an universal manner, units are basically conventions we agree on. And like any convention, they are subject to change. Some quantities are claimed to be unit. For example, we claim a certain length to be 1 meter and then carefully try to duplicate that length to produce meter scales. Sometimes we choose a fraction of that length and come up with a centimeter scale. If you refer to older textbook, the meter is defined as the length of a certain scale made of platinum and iridium and then carefully preserved in a controlled environment in Paris. But there are thousands of things to be measured. So do we attach with everything one unique unit? Fortunately not. We define a minimum set of quantities as base quantities and express everything else in terms of them. They are derived quantities. They might change too, because after all, these are also conventions. Length, time, and mass are base quantities. Unit of these quantities are base unit. However, in 1971, 7 quantities were picked as base quantities in the 14th General Conference of Weights and Measures. In May 2019, base units were redefined. These are the 7 quantities: mass, length, time, current, temperature, amount of substance, and luminescence. Their units in SI system is kilogram, meter, second, ampere, Kelvin, molar, candela. SI system is the internationally accepted system of units. However, there are parallel systems of units which are equally useful. The question remains, why do they keep changing it? Well, as physics evolves, we find out new quantities. For example, when electricity was first invented, people were compelled to have an unit for electric charge, coulomb. As the subject developed, it was found that defining current as base unit is more convenient, so we now have amperes. There is another reason. Base units should be absolutely invariable, so we try to define base units in a way so that it stays in that way for ages. That's why in the first place we chose a scale made up of platinum and iridium, which definitely does not erode with time. Also, we kept that scale carefully in a controlled environment so as to seal it up against any temperature fluctuation. As we know, metals change in length if it is subjected to temperature fluctuations. So, as time goes by, we come up with cleverer ideas to define them as new experiments become available. For example, the meter nowadays is defined by taking the fixed numerical value of the speed of light in vacuum to be 299,792,458 when expressed in units of meter per second, where the second is defined in terms of fixed numerical value of the cesium frequency, which is an atomic clock. A meter is then just 1 upon 299,792,458 of the distance traveled by light in 1 second in vacuum. Notice that in the above definition, a base unit is defined from a derived unit. That is, we define length from speed. This is because the measurement of light speed has become extremely accurate of late. However, it leads to a very curious question. Aha! Length is an optical property. Well, not really. However, if you define meter in the prescribed manner, then certainly it uses some property of electromagnetic radiation. Come to think of it, how do you measure lengths in day-to-day activities? You either use a scale or a measuring tape. Now, if you think carefully, you will find that not all materials are suitable to make scales. For example, you cannot make scale out of water. You need a solid substance. Rubber band is a solid substance. However, it is very much stretchable and thus not suitable for making of a scale. So, as you can see, ultimately, even if you measure length with a scale, it is hopelessly dependent on material properties. Material properties are trickier things, and very often analysis of material properties needs the definition of length. So, isn't it becoming circular? Well, yes. There is no straightforward answer to this apparently simple question. In fact, throughout history, many length paradoxes have surfaced in the theory of relativity. However, we keep it for a different day. For the moment, let us give different commonplace objects and their weights and volumes. Notice there are different weight units: 1 ounce, 1 pound, 1 ton. There are also different volume units: 1 fluid ounce, 1 cup, 1 pint, 1 quart, 1 gallon. As I mentioned earlier, there are many different unit measurement systems. Also, in our day-to-day activity, we come up with non-standard definition of units. This is another curious chart. Here we have electron mass. Electron is the tiniest object freely available in nature. It has a mass of 10 to the power minus 30. On the other hand, in the extreme far end of the scale, we have the estimated mass of our entire observable universe, that is 10 to the power 55 kgs, a staggering difference of order of 10 to the power 85. This is another scale depicting small objects. For example, an atom has an average diameter of 0.1 nanometer, whereas a DNA diameter is around 2 nanometer. Similarly, a virus has 100 nanometer of radius on average. A bacteria is scaled of the order of micrometer, and a sound particle will have a grain size of 1 millimeter. Notice the prefixes. We'll come back to this point. Here is another interesting scale. From the tiniest possible object to the entire observable universe, we put it in a size scale. As you can see, humans are placed in of the order of 1 meter scale. As you can see, we have found clever ways of writing large and small numbers using powers of 10. Another way of writing, say 10 to the power 9, is to write E9, where E stands for exponent. The meaning is obviously the same. Or sometimes we use prefixes, as in the previous case. The prefixes are kilo, centi, deci, etc. Let us, for a moment, consider an interesting situation. Have you noticed? We are using observable universe instead of real universe. That's because the speed of light is finite and so is the age of universe. Speed of light in vacuum happens to be the upper limit of speed 2 that comes from the theory of relativity. That means the fastest possible object is light. So, if you care to perform an experiment, the fastest object you can have at your disposal is light. Suppose your experiment takes 5 seconds. Within that 5 seconds, you can possibly measure the distance up to which light can travel in 5 seconds, not more. So, according to modern theory, our universe has begun in a distant past, but in a finite past. So, only a finite amount of time have lapsed since its beginning. For example, let's consider universe has started 100 years ago. So, up to now, light has traveled only the distance it could travel in 100 years and not more. That means, however large our universe might be, we can only observe up to that distance. That's why the observable universe term creeps in. We will have a separate lecture on cosmology where we discuss these interesting issues in more detail. For the moment, we give you a chart of standard prefixes: tera, giga, mega, kilo, deci, centi, milli, micro, nano, and pico. These are useful abbreviations, and you should keep it in mind. Every now and then, you get to use that. So, the next question is, how do you write something? Do you write 1000? Do you write 1000.00? Or should we write 1 into 10 to the power 3? Well, scientists have decided on a standard way of recording measured data and publishing numerical results. Remember that science is precise, but at the same time, it is not exact. One never comes across an absolute value as an experimental result. For example, in 1972, Evanson and others measured the speed of light in vacuum using laser interferometry. They came up with a result of 299,792.4562 plus minus 0.0011 meter per second. This plus minus 0.0011 meter per second is the uncertainty in the measurement. But we define meter with an exact speed of light, remember? How can I do this? Well, to be exact, the latest measurement of light speed is 299,792,458 meter per second with a measurement uncertainty of 4 parts per billion. However, when we defined meter in 1983, we agreed upon the value 299,792,458. So although it is very close, it is not an experimentally observed value. More on the measurement and uncertainties are to be found in part 2. For the moment, you can do your own research. You may search Wikipedia for 2019 redefinition of SI base units. They have a very good article on that. Although SI system has become standard, there are other unit systems as well, as I repeatedly mentioned. Learn about them from your book. Sometimes they are extremely useful. Learn about the unit conversions. They are extremely helpful too. These days, many mobile have unit conversion apps. You can also find one online. However, you should be able to convert commonly used units on your own. Lastly, specific branches of physics sometimes use special unit systems. For example, high-energy physicists and cosmologists often use natural unit system, where speed of light is considered unity. Google for the term natural units. Have a look just for fun. See you in part 2.